So now let's look at the next way that heat can leave a human body from some overheating athlete, which is conduction. The basic idea of conduction is that in any substance, whether it be a gas, a liquid, a solid, if some area is hot, that heat will tend to spread to the cooler areas. So let's imagine this is a gas over here, and the gas molecules on this side are moving around like crazy, so it's hot, whereas over this side they're just moving very slowly, and so it's cold. What's going to happen? Well, some of these fast-moving molecules are going to whiz down this side and crash into the slow-moving ones and speed them up. Meanwhile, some of the slow ones might just wander over this side and bring down the whole tone on the left. So as time goes on, this motion of molecules or atoms from one side to the other will tend to equal out the heat. Heat flow will flow from once hot to cold until everything's the same temperature. In a solid, it's a bit different. Again, let's imagine that this side of a solid, the atoms are moving really fast, and on that side they're only going very slowly. What's going to happen now is if this atom is moving really fast, it's going to pull on the chemical bond here. So that chemical bond is going to be jerked from one side to the other. So before long, this one's going to be moving fast too. And then it will pull on the bonds and jerk this one. And so by each one pulling on another bond, before long the vibrations will move all the way up and down. In metals, you've got an even faster process. What can sometimes happen is in a metal, because it's got free electrons, if this atom's whizzing around, it might smash into an electron and send that speeding down to the other side where it crashes into something else. The electrons can typically go maybe 100 atoms in one flight up and down inside a metal. So that allows very rapid motion of heat energy from one side to another. How do we deal with this mathematically? Well, the heat flow in one dimension, so we're just assuming uniform temperatures on one side and the other. In 3D is a bit more complicated. We need some vector calculus that you'll see in second year. But let's just do 1D for the moment. Heat flow is going to be minus a constant, the thermal conductivity, times the cross-sectional area. Clearly, if there's a bigger cross-sectional area here, more heat can pass through it, times the rate of change of temperature with respect to position. So if the temperature is uniform, then sure there'll be fast-moving atoms going from right to left, but there'll also be fast-moving atoms going from left to right. And so there'll be no net heat flow. To have a heat flow, the temperature needs to be different on one side from the other. And the more rapid the change, if it's a very hot, very close to very cold, so dt is large and dx is small, then you're going to get a lot of heat flow. If the temperature change is very small, or it takes a very long distance, then you won't get so much heat flow. What is this thermal conductivity? Well, for air, thermal conductivity is about 0.025. The units of this are watts per meter per Kelvin. For steel, so that's for air, for iron or steel, it's much more, it's about 40. Whereas for copper, it's about 380 watts per meter per Kelvin. So it varies drastically. This is why you use copper to conduct heat away from components in electronic circuits, and you don't generally try and use air to do it. So how is this going to work for cooling down an athlete? Well, you've got your skin. Let's assume that blood is carried to blood is passing down veins near your skin, and that carries the heat from inside to the skin. The heat will then have to conduct through the skin, but that's pretty thin, and then into the air outside. How far does it have to go into the air? Well, if the air was totally still, it would have to go far, it would heat up the air nearby, and will keep on heating up the air until all the heat's gone out, to eventually heat up the entire room around you. But that's not going to work in practice. What will happen in practice, even on a perfectly still day, is you get a layer of hot air close to the surface, and that hot air will rise. And as it rises, it'll pull in more cold air below. This is convection. Let me show you a simulation of convection in a room. In the simulation, we've got a room, and I've got a plate that I'm going to heat up. And at the moment, the colour here shows the temperature of the air. So if I run the simulation, you'll see the hot plate heats up the air, and the hot air starts rising. In this case, is a plume. More cold air is being sucked in from the side. Of course, it's a rather more complicated, chaotic process. And before long, you've got whirls and vortexes of heat going up and spreading all the way around. So on a still day, that's what will happen around your body. You'll get some sort of convection. But the air will need to certainly conduct a certain distance into the air. It'll have to get maybe a centimetre or so into the air before there's enough air that can start convecting. On a windy day, things are different. If there's a wind blowing over your skin, the wind won't be travelling very fast very close to your skin because of the viscosity, but it'll get faster and faster the further away it goes. So you just need to conduct the heat far enough into the air that it can be carried away by the wind flow. On a very windy day, that might be only a millimetre, or it might, on a very calm day, have to go a few centimetres into the air. Clothes are basically trapping layers of air close to your body. That's what they do. Clothes, like a woolly jumper or a coat, is basically a bunch of fibres, and the sole purpose of the fibres, they're not blocking the air themselves, they're just trapping little bits of air inside and stopping it from convecting or being blown away by the wind. So hopefully your coat keeps the wind outside, and if the air in one of these little cells gets hot, it can't convect anywhere or move anywhere. So that's forcing the air to have to be the heat to be conducted all the way through the thickness of the clothing. That's what clothes are for. That's why they keep you warm on cold days. So let's estimate how much heat we might lose. Let's imagine that the skin temperature is 36 degrees, and let's have the air temperature as about 20 degrees, so a nice temperate day, not a heat wave. And we'll assume there are no clothes, but it's fairly calm, so the air has to get about 1 centimetre before it's far enough away. The heat, has to get 1 centimetre before it's conducted away. So in that case, the heat flow is going to be minus. The minus in this equation just comes from the fact that the temperature gradient and the heat flow go in opposite directions. So if you're hot here and cold there, the temperature gradient is negative, but the heat flow is positive. So that's all the minus sign is telling you. So it's minus the conductivity, which is 0.025, times the area, which for the skin of a human is about 2 square meters, times d temperature by d position. So it's going to be at delta temperature, which is going to be 36 minus 20, so 16 degrees over a centimetre, 0.01 meters, which comes out as about 80 watts. So you can see that on a 20-degree day, reasonably calm air, you can get rid of most of the heat that you generate just sitting stationary. But if you're starting to do some violent exercise and your power consumption is up to 200-300 watts, you're going to have trouble. Running might help it because it might make the boundary layer of still air thinner. A wind would certainly help. So if you're running on in the nude or dressed in only very thin clothes on a day when it's 0 degrees and a howling wind, you're probably in no trouble. Conduction and convection can carry away the heat. If it's calm, then, and it's especially if it's a hot day, if the temperature outside is like 30 degrees or 35 degrees, then your delta T is going to be much smaller and you're going to have real trouble losing the heat. So can conduction keep you cool? Yes, on a windy, cold day. On a hot day, if it's not so windy, it's really not going to do it. And it's even assuming you've got no clothes on.